For thousands of years, humanity has looked toward the night sky and asked one question above all others. Are we alone? Ancient civilizations imagined gods living among the stars. Philosophers debated whether other worlds existed beyond our own. Scientists eventually proved that planets orbit countless stars throughout the Milky Way. Yet discovering a planet is only the beginning. The real challenge is determining whether any of those distant worlds could actually support life. Today, one extraordinary observatory is bringing us closer to answering that question than ever before. The James Webb Space Telescope is not simply taking pictures of distant planets. It is analyzing the chemistry of their atmospheres, searching for the molecular fingerprints that may reveal whether life exists beyond Earth. The James Webb Space Telescope, often called JWST, represents the most powerful space observatory ever constructed. Launched in December 2021, it operates approximately 1.5 million kilometers from Earth at a location known as the second Lagrange Point, or L2. From this stable position, Webb can maintain a constant orientation away from the Sun, while its enormous 5-layer sunshield protects its delicate instruments from heat. This allows the telescope to observe the universe in infrared light with extraordinary sensitivity. Infrared astronomy is the key to Webb's remarkable capabilities. Unlike visible light, infrared wavelengths can reveal objects hidden behind dust clouds and detect heat signatures from distant celestial bodies. More importantly for exoplanet research, infrared light carries detailed information about the molecules present in planetary atmospheres. Every chemical compound absorbs specific wavelengths of light. By measuring which wavelengths disappear as light passes through an atmosphere, scientists can identify the gases surrounding an alien world. This technique is known as transmission spectroscopy. When an exoplanet passes in front of its parent star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching Webb's mirrors. Although the amount of light involved is incredibly small, the telescope's instruments are precise enough to detect subtle changes in the spectrum. These tiny variations reveal which molecules are present high above the planet's surface. The science resembles reading a barcode. Each gas leaves behind its own distinctive pattern. Water vapor absorbs certain infrared wavelengths. Carbon dioxide absorbs others. Methane, carbon monoxide, ammonia, and many additional molecules each produce their own unique signatures. By comparing the incoming light with laboratory measurements, researchers can reconstruct the composition of atmospheres hundreds of trillions of kilometers away. This capability represents a major leap beyond previous generations of space telescopes. Earlier missions successfully discovered thousands of exoplanets, but determining what their atmospheres contained remained extremely difficult. Webb changes that. It transforms distant planets from tiny points of light into chemically measurable worlds. Since beginning scientific operations, Webb has already analyzed numerous exoplanets ranging from scorching gas giants to smaller rocky candidates. One of its earliest successes involved detecting carbon dioxide in the atmosphere of an exoplanet with unprecedented clarity. Since then, observations have revealed water vapor, methane, sulfur dioxide, and other molecules on several distant worlds. Each discovery improves our understanding of how planetary systems form and evolve. Perhaps the greatest excitement surrounds rocky planets located within what astronomers call the habitable zone. This is the region around a star where temperatures may allow liquid water to exist on a planet's surface under suitable atmospheric conditions. Liquid water is considered one of the essential ingredients for life as we know it, making these planets particularly interesting targets. However, simply being in the habitable zone does not guarantee habitability. Venus, for example, lies near the inner edge of our own solar system's habitable zone, yet possesses a surface hot enough to melt lead due to an extreme greenhouse effect. Mars, meanwhile, sits near the outer edge but is cold and dry today. Understanding an atmosphere is therefore essential before judging whether a planet might support life. Scientists searching for life often discuss biosignatures. These are chemical combinations that may indicate biological activity. Oxygen attracts enormous attention because it is continuously produced on Earth by photosynthetic organisms. Methane is another important molecule because many living organisms generate it naturally. Individually, these gases can arise through non-biological processes. Together, however, particularly when maintained over long periods, they become far more intriguing. Even then, researchers remain cautious. Detecting oxygen or methane would not automatically prove that life exists. Planetary geology, volcanic activity, and complex atmospheric chemistry can produce surprising results. Scientists therefore examine the complete chemical environment rather than focusing on a single molecule. The search for life demands extraordinary evidence supported by multiple independent observations. Webb is particularly well suited to studying planets orbiting small red dwarf stars. These stars are cooler and smaller than our Sun, making planetary transits easier to observe. Because the planet blocks a larger proportion of the star's light during transit, atmospheric signals become more detectable. Several nearby planetary systems have therefore become major priorities for Webb's observing program. Among the most fascinating is the TRAPPIST-1 system, located about 40 light-years from Earth. It contains 7 known rocky planets, several of which orbit within or near the habitable zone. Webb has already examined some of these worlds, helping scientists determine whether they possess substantial atmospheres or whether earlier stellar activity stripped them away over billions of years. Another exciting target is K2-18b. Observations with Webb have identified carbon-containing molecules, including methane and carbon dioxide, within its atmosphere. Researchers continue investigating whether this intriguing planet may possess conditions capable of supporting liquid water beneath its atmosphere. Although much remains uncertain, it demonstrates the extraordinary level of detail now possible. The engineering required to achieve these measurements is astonishing. Webb's primary mirror spans 6.5 meters and consists of 18 gold-coated hexagonal segments working together as a single optical surface. Its instruments operate at temperatures colder than -230 degrees Celsius, allowing them to detect incredibly faint infrared signals arriving after journeys lasting tens or even hundreds of years. The telescope's precision is equally remarkable. During a planetary transit, the change in brightness may amount to less than 1%. Within that tiny signal, Webb must distinguish subtle molecular fingerprints while compensating for instrument behavior, stellar variability, and countless other factors. Sophisticated computer models and statistical techniques help researchers extract reliable results from enormous volumes of observational data. Artificial intelligence is becoming increasingly important in this process. Machine learning algorithms analyze complex spectra, identify faint molecular signatures, and compare observations with millions of simulated atmospheric models. These tools accelerate discoveries while helping scientists evaluate competing explanations for the data. The implications extend beyond astronomy. Every atmospheric measurement contributes to our understanding of planetary evolution, climate systems, and the conditions required for life. By comparing Earth with dozens or eventually hundreds of other worlds, scientists gain new perspectives on how rare or common habitable environments may be throughout the galaxy. Webb also reminds us that science often advances through patience rather than dramatic announcements. It is unlikely that one observation will suddenly confirm the existence of extraterrestrial life. Instead, evidence will accumulate gradually as researchers observe additional planets, refine atmospheric models, and compare independent measurements across many different systems. Future observatories will build upon Webb's achievements. Proposed space telescopes specifically designed to directly image Earth-sized planets may eventually analyze atmospheres with even greater precision. Combined with advances in spectroscopy, interferometry, and adaptive optics, the search for life will continue accelerating over the coming decades. For now, however, the James Webb Space Telescope stands at the forefront of humanity's greatest scientific investigation. Every time it observes a distant planetary transit, it captures more than light. It captures information that has traveled across interstellar space, carrying the chemical history of another world. For generations, we searched the heavens, hoping simply to find planets. Today, we are reading the skies of those planets molecule by molecule. We are learning whether distant worlds possess water, clouds, carbon dioxide, methane, or perhaps even the complex chemical combinations associated with living systems. The night sky is no longer a collection of unreachable stars. It has become a laboratory filled with worlds waiting to be understood. Whether Webb ultimately discovers convincing evidence of life or reveals that Earth is extraordinarily rare, its legacy will be profound. It has transformed one of humanity's oldest philosophical questions into a scientific investigation guided by observation, chemistry, and engineering. For the first time in history, we possess an instrument capable of examining the atmospheres of distant Earth-like worlds with remarkable precision. The answer to whether we are alone may still lie beyond the horizon, but thanks to the James Webb Space Telescope, that horizon has never been closer. If you enjoyed this deep dive into the forces shaping our future, be sure to explore our other documentaries examining the technologies redefining modern civilization. And if you want to keep exploring the biggest questions about science, power, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.